Hello, everybody. I'm Greg Swazer. I am here with the Regional Sustainable Development Partnerships, part of the University of Minnesota Extension. As many of you who are on this webinar now know and have been following, we've been working on passive solar greenhouse technology, winter solar greenhouse technology for the past several years now. And I am pleased to bring Dan Handeen and Shannon Mutschelknaus. Sorry, I will get your name right one time, to talk about thermal mass and moving hot air out of the greenhouse. So to start with, I think we will have Dan give a little overview of the elements of passive solar greenhouses. So here we go, Dan.
Okay. I think I have this ready. Hello, everyone. Nice to be with you tonight. Let's see. So just as far as a general overview of what we're going to be talking about tonight, first, we're going to try and define the essential features of a passive solar winter greenhouse as we are defining them for purposes of this evening's discussion. And so just to make sure we're all on the same page, but I also want to be clear at the beginning that we are going to be concentrating primarily on the thermal mass / heat storage component of the winter greenhouse design. Okay, so I know there's probably people that have questions about, insulation or growing things, all of the other peripheral, related topics and issues that are inherently part of a deep winter greenhouse, but we're going to be talking mostly about the heat storage. Okay, so that's the focus for tonight. Let's try and stay on that as much as possible, because we only have an hour and a half, and I know it'll go quickly. So with that in mind, I have a couple brief slides just to talk about what those essential elements are. And if I can share my screen. Here are a couple pictures of some winter greenhouses, and they all have similar features, even though their form varies so slightly. The primary things or definition, right, that we're folding these under are two major things. One is that we're optimizing for winter production. Of course, these types of structures can be used for, doing starts like you might be doing right now, or trying to, do some tropical production, as Shannon will be talking about in just a bit. But then the other primary feature that we have along with this just being a regular passive solar greenhouse, I mean, in some way, every greenhouse is a passive solar greenhouse, right? The thing is that with our definition, we're trying to capture that sun heat, that solar heat, and then store it so that we're able to use it later on. And that's what we'll be talking about most specifically tonight. Some of the essential elements, if you will, the necessary features of a winter greenhouse are: number one, a glazing wall. We need a transparent glazing wall so that we can get the heat spectrum of the electromagnetic spectrum that's coming from the sun. Of course, we need the light as well, but we're not going to be talking about that so much tonight. There'll be a little, kind of tag at the end where we'll come back to that, but we need that glazing wall, of course. Insulation on all sides that are not glazed. Any side that is not getting us any solar income or solar heat income in terms of the energy balance of the space, we want to try and keep that heat in, right? And so especially the north side, obviously, the roof, and then the east and west sides, because we're optimizing for winter production, when the sun is lower in the sky, generally, we're not going to get very good light from the east and the west. So we're optimizing for getting our glazing getting our sunlight coming in from the glazing wall on the south side primarily, and then insulating everything else. Three, a means of heat storage. We'll be talking all about that this evening. So, and so Shannon and I are going to go over kind of what we're calling a survey of different heat storage methods. You've probably been scouring the internets for different types of ideas and seeing different ways that people have done it. So we'll try and hit all of that, maybe talk about some of the pros and cons of each one, and then we'll go more specifically into the heat storage methods that we're most familiar with. and talk about some of the performance from our respective greenhouse projects. And then the last one I'm putting in here as a necessary feature is ventilation. And of course, we're trying to keep as much of the heat in the greenhouse as possible so that we can store it, we can bank it, and then reuse it later on when we need it, when it's cold, nighttime, cloudy days. But we're probably going to have times where we're getting way more incoming solar radiation than we're able to effectively cram down into our storage device, right? And so we need to exhaust that excess heat, and we need to do that through ventilation. So it's something that might be commonly overlooked as people are getting excited about designing their winter greenhouses. So that I think pretty much covers the necessary features. So with that, I'm going to switch over. Fingers crossed, I won't have the same sort of issue with getting this one up and running. So, okay. Keeping an eye on the question and answer as well. I don't know, Shannon, do you want to look those over as I'm getting this survey?
I can read one to you if you like. When using a rock box for heat storage, I saw poly wrap. I know you want to prevent heat escape, but how do you prevent mold buildup within the box? And secondly, if it's a sealed insulated box, isn't the back pressure preventing warm air from pipes from entering, as there's nowhere for the air to flow through?
I guess I don't quite understand the question.
I think there's maybe two things in here. He's asking about mold buildup, which is a good question. Usually the continuous airflow reduces mold buildup. He's asking about polywrap. I'm not sure if does one of the rock box designs have polywrap insulation or something?
I'm not.
But with the back pressure, so on the rock bed system, there's an intake where the fans are either on the intake or the exhaust. So there's an intake and an exhaust, so you don't have a lot of back pressure, so that the air will flow through it easily. So maybe we'll have some pictures and illustrations later kind of showing where the air goes in and out to probably help with that. And then Bob asked, how much UV percent do you lose with curved glazing, like in one of the 3 greenhouse picks? He's going back to on the slides you had, Dan. Mm-hmm. And like Dan would say, the flat face glazing material is really optimized for a particular part of the growing season, the winter time. And so if you're going with a greenhouse structure that has a curved glazing, it's typically more multi-purpose or year-round, and a little bit more optimized for just overall sun capturing and not just a particular season.
Yeah, there's a question about glazing options. If we have time at the end, maybe we can talk about that. But again, we're focusing on the heat storage methods this evening. So I did want to make sure that we hit this. Greg, I don't know if you brought this up, but we've got a ton of information on the extension website. Please check that out. But some methods of heat storage. And I think this next kind of distinction will talk about one of the issues that that Bob's question brought up here. Can you give an example of rock box size and typical time it takes to charge from point of new install to fully charged? And so I think this might be one of the clarifying points that might be helpful. So we're looking at different scales of time, right? Different periods of time that we're trying to capture and store heat. And one thing that has been done, I don't know if it's frequently, but something that's been attempted frequently, especially in residential construction, where we saw a lot of efforts to try and reduce energy consumption or get off grid, was to try and do what we call seasonal energy storage, right? And so you're storing all of this sun's heat in the summertime and trying to, store that so that we can use it over the wintertime. And generally those are pretty tough to balance. And, I've seen firsthand results. They're expensive. They're very slow moving, as you might expect. But on the other side of that, one of the installers of those types of systems said, just embrace the slow. Just accept that that's going to be part of the performance of it, and that's fine. However, this said, even the best designed one that I have seen gets them into about end of November, right around the holidays, as far as heat storage. So really still the coldest parts of the year, they're not able to capture all of the heat that they might need over the course of the entire year. So then the other type of heat storage, or the other kind of scale of heat storage that we're looking at, is diurnal. And this is primarily looking at what's available from day to day, right? So it's really sunny one day, we're trying to capture that sun's heat for that day, store it as much as we can, and then try and take the edges off the peaks and valleys of the temperature in our growing space. And that's primarily what we're talking about today. However, that said, of course, depending on how much mass we have, we may be able to go for a couple days, we may be able to go for a week or two. So there's kind of a gray area in there. And I think we can come back to this question about how long it takes to build things up. So those are the kind of two scales that we're looking at. Then, as general categories of types of heat storage, there's a number of different methods. And more broadly, we could divide these into three categories, one being water or glycol. We'll talk more specifically about each of these in just a second, but storing them in containers or tanks. A lot of people ask about integrating aquaponics or hydroponics into winter greenhouses. I think they're totally compatible technologies. However, I would not rely on using the water that you're using for the hydroponic or aquaponic operation as your heat storage method. I know it seems like a great idea, but generally you're not able to recapture that heat in a usable form out of the tanks that you're using for your production. And another side note is that fish don't like fluctuations in temperature. And so I've seen firsthand fish kill in a winter greenhouse with aquaponic operation in it. So out of respect for the fish, please don't do that. Another category would be phase change materials. And these are materials that literally absorb heat when they go through a change in state. And so one example would be a wax changing from a solid to a liquid. It takes heat to have that happen, and the reverse happens. So the classic example I use is, playing with some wax on a candle or something, and you stick your finger in the molten wax and it just is super hot because it's literally giving heat off in that solidification, right? When it turns back into a solid, it's injecting heat basically, or giving off heat back into your finger. So that's one way that we can store heat in phase change. And then the last one that we'll be talking about mostly today is storing heat in mass. And these are, as it would imply, simple things like brick, block, stone, soil, and rock. And of course, there will be instances where we have water in some of those places, and that acts as both a phase change and as a kind of heat storage in its own, right? Which brings us to this slide, which I think is helpful for us to keep in mind, just about the heat capacity, or the specific heat, it's also called, of various materials. And looking at the ones that are more commonly available to us, I put some other ones in here just as a comparison, a point of comparison, like ammonia. I know we're not probably going to be using ammonia as a heat storage method in most of our greenhouses, but it is interesting to see the capability there. Generally, a higher number of specific heat or heat capacity holds, quote, more heat energy. It's interesting to see that some of the more conductive materials that we notice or we would consider actually don't store much heat as well. Like we think of a cast iron pan or something, it conducts heat very well, but it's actually not very good at it can't store very much for the amount of material that's there. So if you really want to dig into this, there's some calculations there. And Shannon added some densities, which I think are important for people to kind of put in terms of how much stuff you might need. So Shannon, go ahead. If you want people.
Yeah, like I thought, one thing when you look at the CP or the specific heat value on the previous slide, you'll see air is like somewhere, it looks like a pretty significant number, but that energy storage number is per kilogram. So how much air you need to make a kilogram is quite a lot. So it's a little bit easier to think about your heat storage capacity in what's called heat storage density, which is the amount of heat required to change the temperature volume of material by 1 degree, which is the difference there. And I apologize for our non-American friends. I put this all in American units or British units here so that folks could use these numbers a little bit easier. But you can see with air there, for example, it ends up being 0.018 BTU per cubic foot per degree Fahrenheit. So for every degree Fahrenheit you heat up your air, this is how much heat your cubic foot of air holds. And this really explains why in the greenhouse you have this issue with, oh, the sun comes out, oh, now it's super hot, I just burned all my plants. Or the sun goes down and it cools off really fast. It's because that air just doesn't hold very much heat. But then when you look at some of these other materials, everything holds a lot more heat than air does. So you can see concrete, really one of the best materials just as a thermal mass. Water is great, holds a lot of heat. So it takes a lot to heat that water up, and it takes a lot to cool it down. Then we have 2 numbers in here. If you're using a soil-based heat storage system, the heat storage capacity depends a lot on how moist that soil is. And so you kind of see the range between a really water saturated soil, might be 39, and a really dry desiccated soil would be all the way down to 15. And then granite, some type of stone, if you have no air perforations in it, somewhere around a 31. So it kind of gives you a perspective of the range of heat storage capacity comparisons there. And then I just threw in some calculations if someone wants to play with these numbers on their own for whatever their greenhouse size is, how to calculate that, convert that into BTU. So for this example here was a 15 by 30 foot greenhouse. That's a 4 foot deep thermal mass in wet soil. So if you calculate that out and you heat it from 50 Fahrenheit to 65 Fahrenheit, which would be a pretty reasonable thing you can do. It's actually 15 degrees, not 10 there. Gives you 456,300 BTU of heat that you just stored. Pretty awesome. That is actually almost exactly the same amount as a 20-pound propane tank as far as the amount of energy that holds. So kind of put that in perspective. That's what that can get you. And I think this goes back to one of the questions we had. Someone asked for clarification that Dan had on, well, why can't I store enough heat to last me all winter? Well, you need to have a really, really large mass to store enough heat for all winter. So it's pretty challenging to do that. Even if you have a large water-based storage system, storing it from July and August to get you all the way through our winter is pretty challenging in our regions.
And I think that brings up another good point that kind of stems from this slide. This assumes like perfect ability to, put that heat into your storage mass or whatever it is, and then perfect ability to get it extracted back out, right? And so part of that is the interface, how we've arranged whatever exchange mechanism that we're, putting the heat in and getting it back out again, which is historically one of the challenges with large scale seasonal heat storage stuff, which is, how do you make sure that you've quote saturated or charged up this entire mass with, with as much heat, and then how do you get it all back out, right? heat moves a lot better when there's a high difference in temperature. Once it starts to get within a couple degrees of your extraction fluid, it doesn't really want to move there. So that interface is challenging too. So another common one is using water, or more commonly glycol solution. So we've got, of course, some kind of antifreeze in there that helps just in case the temperature should get down below freezing, and it also helps with any corrosion and so forth. And so people use milk jugs, people use old 55-gallon drums. There's been a number of research projects related to using clear columns and so forth. Generally, these aren't quite as effective because they're not actually absorbing the radiative portion of the spectrum as much. If you think about it, when sun hits a black surface, it's actually absorbing more of that energy into directly into the surface. And in the case with a clear column, some of that is actually passing right through. So ideally, it would need some sort of black surface or a black fluid in there, really, to make the most use of the sun's radiation that's hitting that surface. So I don't recommend using clear stuff. There's also, very commonly issues with algal growth and that sort of thing in containers. So unless you're going to be like pouring bleach in there, it's not really attractive either. So it depends on your aesthetic. Maybe you're into that sort of thing. But might as well just go ahead and paint your containers black if you're trying to store it in heat. Or I'm sorry.
We had one question from Sandy Taylor. She said she had plenty of firewood. She asked, has anyone ever used heat storage with the fire? And actually, that's a really common thing if you have a wood-fired boiler, because they put out a lot of heat really fast, usually more than you can use. So there are usually water storage systems that are commonly used in hydronic heating systems like that, because a fire is very hot for a short period of time, then it goes out. So it's very common to store that. And you actually can buy off-the-shelf storage tanks for wood-fired heating systems like that. So go ahead, Google around for that, and you'll find a lot of them off the shelf. Now you'll find that it takes up a lot of space. They're really large. You can get them in a rubber bladder that you can make your own box and fill that, or you can buy plastic ones, and they got to be insulated so you don't lose that heat.
I've also seen examples of it's a combination of a rocket stove with a mass heater, and they actually run the mass heat or the exhaust from the stove through the north side of their greenhouse and put mass around that. Usually just fill it up, a box full of rocks around the exhaust flue essentially, and store the heat that would otherwise be just going up through the chimney in that. So there's a number of different approaches to using wood. And then a last note here, rainwater catchment. A lot of people are curious about using that or incorporating that as some kind of thermal storage. Again, I don't recommend it because it's, generally you've got, anytime it rains, it's going to be cold water generally, or colder than you want to have in there. And you're going to be spending a lot of energy trying to heat up that cold water that came in. So I would generally keep your thermal storage fluid, whatever that is, separate from your catchment and irrigation sources. So let me check here quickly. Does glycol increase water's heat capacity? I think only very slightly.
Just a little bit.
Yeah, just a little bit. When they were designing tiles for the space shuttle, one of the material scientists said that black was not necessarily the best color for either absorbing or reflecting heat. Has anyone looked at color absorption? I do have a slide at the very end to talk about that. Of course, we do want to try and balance that. The quick answer is we want to absorb heat, but plants need light. So generally, we're going to try and capture the heat in another way rather than storing it in the black interior surfaces of the greenhouse. That said, we have situations like the image that's up on the screen right now, which is, you can kind of see these this textured interior surface of this particular greenhouse. This is the Suncatcher model greenhouse, or I'm sorry, the Carolina Mountain greenhouse designed by Suncatcher. They're out of, I believe, North Carolina. And they have used these blister packs of phase change material on the interior surface of their greenhouse. And so these, of course, are directly exposed to the interior temperatures. And when it gets too hot in there, they can change state, basically move from a solid into a liquid, and then they store that heat, and then they re-solidify during the nighttime, and they release that heat back into the growing space. Typically, these are a type of a mixture of different types of waxes and paraffins. Usually it's a mix of some petroleum-based and some actually bio-based lard, essentially, byproducts of beef, the beef processing industry. But the cool thing is they're able to actually tune what's called the Q temp, or the temperature at which these PCMs change state. And so if you know exactly what temperature you want your greenhouse to remain at, they can, you can place an order for this type of material. I don't know about cost right now of PCMs. Generally, it's been somewhat prohibitive in the past, but obviously, these folks did it, so it can't be astronomical. And what's average longevity of PCMs? I think the last time I looked, it was like 50,000 cycles or something. I mean, it's really, really a long time. What's the name of the company with the phase change material greenhouse? They're called Suncatcher. You can see the web address down on the bottom of the slide there. The phase change company, I believe, is called BioPCM, BIOPCM. If you want to just go direct to the manufacturer. They also have different types of encapsulation methods that aren't just these blister packs. Okay, let's see, what else? So let's look more specifically at the mass category of thermal storage. And there's a number of different terms, brand names, all of these are basically referring to the same types of systems, right? Where we're using some type of exchange to heat up either earth or soil, and then, basically extract that heat back out for when we want to use it. And so the thermal mass in these cases absorbs and releases heat with the intention of stabilizing the temperature, right? So we're not just looking at only banking the heat for when it's cold, but we're also looking at the ways that it can help cool off the interior temperatures when it's too hot in the greenhouse. So it does kind of work in both ways. Let's see. Yeah, you're probably familiar with a lot of these if you've been Googling around. And I'm agnostic. I know that the GAT system here is trademarked by Ceres. I love Ceres. They're an awesome company. Definitely go check them out. But many of these are referring to the same types of systems. So Shannon, why don't you go ahead, and I can advance the slide when you want.
Oh, sure. Yeah. So this is covering some mostly passive systems. There's really two really common categories that you'll come across out there. The first one, the general term for it is called a direct use low-grade geothermal. So with this kind of a system, your tubes are usually buried below ground outside of the greenhouse, and they're going to be drawing the heat that is stored in the ground throughout the whole year through the summertime. It's going to be pulling that air in through your greenhouse. So you're not making storing anything from your greenhouse, but you're really using what's accumulated in the ground over time outdoors. And then the next common type here, Dan, is a ground-based heat storage system. Like Dan alluded to, there's all kinds of names for these, which makes it really confusing for folks. There's climate batteries, there's a ground air heat transfer, there's ground something, transfer something, subterranean heat something, and all kinds of acronyms. And there's actually a lot more than this, as you kind of see by Dan's slide before. But this system is a little bit different. In this case, you're taking the heat that your greenhouse is capturing from the sun, because it's getting way too hot in there, and then you're storing that heat in the ground beneath the structure so that you can withdraw that heat from below the greenhouse in the nighttime or on cool, cloudy days like we had today. So there are really two categories. I'll typically refer to number 2 here as a climate battery. It's easy to say, and I think it captures reasonably good what it does. It stores heat, and you take it right back out of the battery. And the low-grade geothermal is also a neat design, and is kind of an illustration of what that looks like.
I think maybe one important distinction, or one way to conceive of them, is that this one is really relying on just the kind of stable temperature of the earth as it is. Whereas all the ground-based heat storage, they're looking at actually trying to change the temperature of that portion of the earth underneath the greenhouse. And so typically you've got some kind of insulated box underground where you're trying to actually retain the heat. You've got a actually big difference in heat from one side of the insulation to the surrounding soil.
Yeah, so for example, in our region here, the natural soil temperature about 30 foot down will be 45 degrees. If you go south of us to Nebraska, maybe you get to 50 to 55, which is actually a really big difference for growing plants. And if you go farther north, your ground temperatures are even going lower and lower than that. So it's very limited on the amount of temperature you can get up to in a direct use low-grade geothermal. Whereas in a climate battery system, in mine, for example, I've been able to heat the ground temperature below the structure up to the 70-degree range. And right now, I think I looked at it yesterday, is like 63 degrees is the ground temperature. So that's well above what it'd be able to get with low-grade geothermal.
Shannon, since we're here, there's a question in the Q&A. The earth tubes are not perforated, correct? And I think you're probably most familiar with the Citrus in the Snow Russ Finch design most recently. So
yeah. Well, both systems will use perforated tubes, and it's really important because you're going to have a lot of moisture condensation in either system, and you need that moisture to drain out, or the tubes will fill up with water from condensate, and you won't be able to blow air through it. So both systems use perforated tubes for the heat exchanger tubes. Usually the manifold tubes on the end are not perforated.
And we'll see some examples of that in just a little bit here. So some pros and cons of each of these types of systems. So with the outboard heat storage, if you will, still pretty simple components, low energy input. Typically, again, as with both of these examples, or many of these examples, we're just using a fan to circulate air through the system. Typically, we're digging down a little bit deeper with this because we're trying to get well below the frost line or any kind of seasonal fluctuations in temperature above that. Of course, we can't have any water in there since we're using perforated tubes. We want water to drain out. We definitely don't want water to be coming in. So we need to make sure that our water table is below where we're burying our tubes. This is still, as Shannon mentioned, this is dependent on your existent ground temperature. And of course, like any of these heat exchange systems where we're using soil or rock, we need tube and fan sizing to be proper so that we're balancing the amount of airflow with what we need in the greenhouse with what we can comfortably move through the ductwork system to get a good exchange of heat. Some other variations that are just worth considering. One is a water-air heat exchanger. Shannon, which one is this?
Yeah, so something that people might do with a low-grade geothermal to get your heat higher is they'll have a water-to-air heat exchanger, or you can use a ground source heat pump. So what you do in that situation, in our northern climates, you might be familiar with from your home, you can't use a heat exchanger to heat your house all winter because there's a point where our outside air temperatures are getting too cold and we can't pull heat from the outside air anymore. So what you can do with the low-grade geothermal is supply air from your tubes below ground to the heat pump, to the heat exchanger, and then bump that temperature up for your greenhouse structure. And so there are situations where folks have done that. Of course, you're even less passive when you start doing that, because you are adding electricity to concentrate the heat that was basically in the ground. And that's really what's happening with geothermal that you're used to. Like, you might have wells drilled. In that case, you have a water pumping through your geothermal system, going through either heat exchanger or a heat pump, typically, to concentrate that heat to a warmer temperature that you want to keep your house or your greenhouse at.
And there are examples of year-round greenhouse operations that have used ground source heat pumps, but they were actually using a kind of more conventional, double layer poly, and it was really expensive to run. So it was concluded to be not effective. And the basic operation for the other types of systems, ground or soil-based heat storage systems, we've got daytime heat coming in. It's being stored in the greenhouse. We take the hot air, we blow it through either ductwork or directly through a rock bed. We heat up that storage medium, and then that air gets recirculated back into the space and continues to circulate, heating up and cooling off as it moves through the mass. And as I mentioned before, we can get quite a bit of cooling in this particular instance, where we might have potential overheating in the greenhouse, where since the air is getting cooled off as it passes through the storage media, then it's coming back up into the greenhouse and effectively cooling that off, or taking the heat out of there, right, as it's moving back down in. And then, of course, at night, we're trying to extract heat out of the storage medium and bring it back up into the greenhouse, right? Pros and cons, typically, again, very simple components, similar to the other system. Still typically pretty low energy input. We're running a couple fans, so that's why we say these are mostly passive systems. Of course, purely passive solar systems don't require any additional energy inputs, right? But we're using the fans to move a fluid, essentially moving the air, right? And so we have to have a little bit of energy that we're using in the system to move this around. Typically, we have better heating capacity if we're in high sunlight regions, if we're able to capture that solar incoming solar radiation, and then effectively charge up our mass. It does provide some cooling, as we've talked about. It doesn't require additional excavation outside of the structure, and so we don't need to be either digging trenches or boring holes down to extract a larger field, or creating more surface area of geothermal contact, right? However, we do need to dig down a little bit, for the DWG V2.2 that we came out with a number of years ago. That was suggested to go down 4 feet. Of course, like the other ones, water table must still be below the tube depth. So we've had instances where people have actually slightly raised the level of their entire greenhouse so that they could make sure that they were above the water table. And then, of course, we still need to have proper tube and fan sizing to be effective. So we'll go into a couple different types of storage methods, and then we'll get into some of the meatier stuff that Shannon and I each have. So one way to make sure that we're getting airflow down into the system is by using either branched or distributed ductwork. And both of these are showing different types of ways of getting air down into a manifold. In this case, they've taken an old 55-gallon plastic barrel and drilled a bunch of holes in the side, and then they've got couplings that attach to that. So essentially, they're going to be bringing air down into this barrel, and then it gets distributed through each of these through each of these ducts as it goes through. Typically, we'll see a number of layers of these ducts as they go through soil, through the storage medium. So maybe this layer will be down here, then it gets a layer of soil over that, and then another layer of ducts. You know, and depending on how ambitious or deep you've dug, you may have, you know, 3, 4, 5 layers of ducts. Here's another example of a manifold. So this is their intake manifold. This is a 24-inch drainage tile, and then this goes into obviously a number of ducts that then go underneath this quite sizable winter greenhouse in South Dakota here. So again, these are using soil in an insulated manner, right? Also, there's another approach here. Again, using just kind of a typical greenhouse structure above and really trying to just use the soil as the storage medium. And you know, this does work, but of course you're losing a lot of heat out of this structure anytime the sun isn't shining. So of course we need the glazing to be able to allow the light to come in and the heat to come in, but it's a liability anytime we don't have that coming in, right? We're losing more heat out of there than any of the insulated parts of the structure. So this is an example of a heat storage. This is basically a big manifold down here that they have along the sides of the just a regular hoop house, essentially. So some considerations looking at designing a thermal storage system, and we'll talk in greater detail about these. Of course, whether you're trying to do seasonal or you know, shorter term, kind of diurnal, or maybe a couple days, week-long heat storage, whether doing active or passive extraction, this is using some type of fan, or if you're just letting the heat kind of just naturally migrate up out of your storage medium. Making sure that you've got good airflow through there, having adequate but not too long tube length. And Shannon can talk about that a bit with his CFD models. And using continuous headers and trunks so that we've got good distribution to all of the transit ducting, or to the rock bed, as I'll talk about in a bit. And then, as Shannon mentioned, having perforated ducting. We expect that there's going to be condensation. We know there's going to be humidity in these, right? This is a greenhouse. We expect humidity to be in there. It's a warm place, so you know, air or moisture is going to be carried in the air. So when it hits cooler surfaces, it's going to drop that moisture out, and we need to make sure that can exit out. Just as kind of an aside, we've done some testing on microbial growth and microbial airborne microbial activity, and it has all been under concerning levels in greenhouses that use rocks or non-perforated tubing as their media. But we can talk about that more at another point. And then last thing, looking at where our intake and our exhaust points are in the greenhouse due to either trying to encourage or trying to discourage temperature stratification and the natural tendency of warmer air to be more buoyant and move to the surface of things, and then how interior air moves within the greenhouse. And Shannon has some nice slides relating to that too. So with that, if we don't have any open questions right now, I will turn it over to Shannon. You're muted.
Hey, can you hear me now? All right, good. And you can see the screen. I'm sharing the right one.
Yep, all good.
Right. Yeah, so I'm going to cover a year of operation. I got my structure going it was January 1st of 2020, and I captured a lot of data as part of this project. So I'll cover a little bit about me, my farm, and the research project, cover some of the details of my prototype and analysis, review 2020 performance data, and then kind of summarize some design guidelines that you can take away and hopefully use for your own projects. So a little bit about me. I'm a mechanical engineer with 20 years experience doing thermal design, research, and testing of electronics megasystems. I put this together right before the Super Bowl. So this is one of our display systems. that we built here in South Dakota and Minnesota for the Raymond James Stadium in Tampa, Florida. These guys are big, they produce a lot of heat, and we got to do a lot of thermal stuff to keep them running in regions throughout the world. I also run a small farm. I'm owner-operator with a fruit obsession. I wonder how many people can identify that flower that's beside my face, I guess, there. Go ahead and type it in the chat if you know what it is. So on our farm, we have quite a few fruit trees. I do this work in greenhouse technology. We raise Scottish Highland beef, and we have Jacob sheep. We sell fiber and products from those guys. So what I'll be talking about tonight is my research project. This was part of a SARE grant. Right here's the number. If you Google that, you'll probably get to the research page. This is completed and all the data is there and published. You can check that out along with variations of this presentation and maybe a little bit less data because I did add a little bit of slides to this. So my objective was to produce data regarding design trade-offs of passive solar greenhouse features, as well as demonstrate a selected design. Many of you might be like me, kind of frustrated with the amount of information or misinformation, confusing stuff out there. There's all kinds of conflicting ideas, and it's hard to tell what is exactly the best thing for the situation. Motivation. So we live in a cold northern climate that really prevents year-round crop production and makes greenhouses too costly, especially for tropical produce and maybe most produce. So I guess traveling around, I got introduced to an amazing array of things I had no clue existed for a lot of reasons. They maybe don't have a long shelf life, so they can't be shipped to our region from where they do grow. One example here that I like is it's actually an Atamoya, but you won't notice that. Just pictures I had. A Cherimoya, I have some Cherimoya trees in my greenhouse, which is why I picked that. And according to Mark Twain, they are the most delicious fruit known to man, but not known to very many of us northern men. They are a delicious velvety flesh fruit. Its custardy is a blend of banana, pineapple, and maybe strawberry flavors, and they're really delicious. If you ever come across one, try to pick it up and get a taste of that. So now I'll cover some of the details of my design. So here's kind of a CAD model of what it looks like. And then up in the corner here is a picture of the finished structure. So we've got south-faced polycarbonate glazing. That's curved trusses because my intent was for year-round production, growing plants and things. The north wall is insulated, as is typical for year-round solar greenhouses. And then insulation here is below grade for the climate battery storage system. I have passive intake vents at the bottom here and exhaust vents at the top that automatically open and close when they need to let out excessive heat. And then elements of the climate battery storage system with the tubes buried in the soil below ground here. Fans are on the north wall. I start off with the hot air intake up here at the ceiling. So we kind of covered these slides here already. This is talking about how a climate battery functions, stores excess daytime heat in the ground for withdrawal at night. So kind of breaking down some of the elements of a climate battery. There's a bunch I'm not going to talk to a whole lot about. We kind of talked about storage medium already. I'm not going to talk about thermostats or fans or blowers tonight. But what we will talk about is the battery insulation, the heat exchanger tube sizing and stuff, and intake and exhaust manifold layouts. And then as well as the intake placements. So I did a bunch of engineering simulations looking at some different configurations that we could do for insulation. Really looking at, what's the cost and when do we get a return on investment for our application, what should we do? So these illustrations up here show the engineering simulations each of these is a constant temperature line. It's called an isotherm. And you can see in this illustration, we've got the foundation, and this is the temperature through the soil. This is the foundation buried below, and then I assumed 70-degree temperature inside the storage system. And so these are the different things that I analyzed in the calculations, starting off with no insulation. This here shows the heat transfer vectors. So basically the size of this arrow tells you how much heat, or the amount of heat relative to that image, is being lost. So you can see where the greatest amounts of heat transfer are occurring out of your storage system. Usually, like maybe Dan alluded to too, is oftentimes kind of forgotten. If you're going to store your heat, you got to insulate it so you keep that heat there. It's particularly important. So these are the three maybe really basic ones where you can put just one layer of 2-inch poly on the outside foam board, up to 4-inch. And then I was looking at, our heat loss is still quite a bit through the footing. So, what are some things we could do to improve that? So you can add what's called a skirt to the bottom of that, where you put basically horizontal insulation to help reduce that heat loss out of the bottom. So did a couple different variations here, looking at 4 foot of frost skirt and 2 foot of frost skirt here on this one. And then I did also design where I put it maybe the more typical location that would be used for these. So frost skirts are a concept that's originally pioneered for areas where you don't want to dig your footings as deep, maybe for whatever reason, for cost, or maybe you have something in the way where you can't dig deeper. So you can use a frost skirt to prevent the bottom of your footing from freezing. And putting your insulation at this level does that, but it is not nearly as effective as reducing your heat loss out of your storage battery as if you were to put it at this depth. So what I ended up doing for my construction project was doing the 2 foot at the bottom of the foundation here. And I really did that because I already had that much excavated, didn't add excavation cost to do a 2 foot. And the benefits of the 4 foot just are not worth the excavation costs from what I found. So I really, from this, I'd say eliminate, maybe these 3 options are probably not great ones. No matter what your climate, you probably don't want to use one of these options, but any of these other ones are good options based on maybe your climate, your growing zone. And I'll show a slide later kind of summarizing based on where your install might be, what would be the most return on investment for that installation. So then looking at the manifold layout, here you kind of see a cross-section view showing those. So what happens in the system is the airflow pattern goes in this tube, comes down, it goes through the bottom layer, and that bottom layer then exhausts diagonally crossed from it up here on the south side of the structure. And then that air comes out, and then it gets pulled into the next closest inlet, and you get a really nice uniform distribution of air throughout the structure because it's going in that kind of a circulation pattern. Another nice benefit of that layout is the heat distribution in the soil storage medium. So you can see if you're withdrawing heat, you have cool air coming in, and it will withdraw heat across that grid out to the hole. So you get a temperature gradient, something like this, where your cool air is on this side and your warm is on this as that air is extracted out. And then your layer right below it is going to be following that opposite pattern, so you can maximize the uniformity of your heat extraction and maximize your usage of your storage medium. So one of the things I did as part of the study was looking at modeling of the airflow rates or the velocity through the different heat exchanger tubes. And what you really want to do is to keep that air uniformly flowing through all the tubes as fast as you can without getting a lot of air moving through some tubes and not the other. which is maybe a little bit harder than you might imagine because air wants to take the easiest path that it can. So here you can kind of see the actual photos of the installation, kind of see what those tubes look like. Looking at some of the different designs I went through in simulations, I thought it'd be pretty easy to run the manifold tube in straight at a 90 into here. So the fan would be up here. We're looking at it from the bottom view. And what you see happens is air comes in and it moves through most of the tubes pretty good. But this one here is this blue color, meaning you're not getting airflow through it. And that's really happens when you come in at a steep 90 degrees. The air has so much momentum that it can't take the quick bend and doesn't want to go through that tube again. So you lose a little bit of heat storage because you're not moving your hot air or your cool air through that part of your thermal mass. So a little better way to do that is to plan to have a 90-degree bend at the end of your manifold and give as much of a radius as you can reasonably do. But that gives you a much more even uniform flow across here relative to this one, but you still, of course, have some gradient. And it's pretty hard to prevent any of that. But one thing that I did do to help with that a little bit on this tube here, which is the lighter blue, which is more velocity, is less velocity. You change the this tube here to come around, so you're constricting the flow by making this a smaller diameter through this portion, and that'll improve the uniformity of your airflow a little bit and give you a little bit more even airflow through the system. But overall, it's pretty good. Definitely much better than the starting one. So then, as far as tube spacing goes, I spaced out the tubes at a 2-foot spacing, both 2 foot between the layers, and then 2 foot here between the heat exchanger tubes. Now, one of the things I was frustrated with is I couldn't find any good information that gave me much technical data on what the trade-offs are with tube spacing. So this was based on the best information I could find at the time. And I'll show you some better info later in this presentation with those trade-offs. So like we talked about, the cross tubes are a 4-inch corrugated perforated type. The manifolds I used were 6-inch because that's what I could get easily available. It would be much nicer to have a larger diameter tube, but it's not quickly off the shelf in your local store, most likely. So, basically the benefit of spacing the tubes closer together, it will allow you to increase the speed that you can charge the battery or discharge the battery. But of course, there's some trade-offs. It displaces more of your storage medium, and it costs more money for more tubes. There's a few pictures of what it looked like. This here is the bottom 4-foot layer, and this is the upper 2-foot deep layer. So did the system work? So this here, I captured a couple days, 2 days of data here that I thought were fairly representative of nice variation. So the first day here was a cloudy, warm day, February 12th of 2020, actually. We had a temperature high of 29 degrees for February. It's fairly warm for us. Then the next day was a much colder day. Overnight, it cooled off, and this was actually ended up being our coldest temperature outdoors that we recorded in 2020 was -23. However, that day was a nice sunny day. This here top graph is our solar radiation levels. So you kind of see it was short here, higher, taller numbers up here. And then I had shaded in the background, this green band is when the fans kicked on to store heat in the soil. And then this reddish area here is when the system is extracting heat from the climate battery. You can see even on this really cold day, we had -23, and it warmed up a little bit. Didn't get above 0, but it warmed up that day. But we had sunlight, and it's usually what happens in our climate is we have cold days, but then our air can't hold the moisture, so we usually don't have clouds, and we end up with sunny days. And yeah, it got to 98 in the greenhouse, pretty warm. So yeah, so kind of comparing these two, you can see when the fan is on and off. The total amperage of the fans is 3.3 amps. And then you can use that and you can calculate what your energy costs were for operating that system. So the time the fans are on this day, it was 20 cents of electricity to operate that system. And on this colder day, which really the fans were almost on the whole time, it was extracting heat. And we had a little bit of time where we were in between, and then we were storing heat with the fans running a lot. So that ends up being 77 cents per day. My greenhouse size is a 16-foot by 28-foot. I think I have those dimensions somewhere. Maybe I cut that slide out. This bottom graph here shows the amount of sensible heat transfer that the system is extracting from the ground. Here at this point is 7,441 BTU per hour. So, it's not a lot, but it's significant and enough to keep the greenhouse fairly warm. So we got fairly warm depending on what you're growing. So on our -23-degree day, we had 38 degrees as the bottom temperature in the greenhouse. So pretty good. A lot of plants won't be killed by that. Some plants will. You're not going to be growing super tropicals like chocolate. Theobroma cacao won't grow in that. That will be damaged below 50. So that's hopeless. But a lot of things will grow well at those temperatures. And then, yeah, and this here is actually the amount of heat that it's storing during that the sunny part of the day. So comparing that same size structure to a typical greenhouse that's either made of glass or a single layer 6 mil polyethylene, that would have cost $5.40 to heat it to the same temperatures that this system did. So that's a pretty good cost savings. Maybe you have the exact same structure, but you want to use propane, which is one of the more reasonable energy sources you could use to heat it. Now that would have been $2.11 per day to heat the structure to the same temperatures. It kind of gives a nice comparison of that. So looking at 2020 in review, the whole year. So this is starting from January 1st, which is when I got the system first operating. So I went into that winter season with no heat stored, no heat banked into the ground to start from, other than what was naturally there already. So the solid dark line here is the average temperatures in the greenhouse, with the dotted line being our average temperatures outside. And the green, the red and the blue here shows what the temperature extremes during the day were. So the highest and the lowest temperatures that we had in the greenhouse. And actually here's February 13th, our coldest day of the year. So throughout the whole year, the operating cost for electricity was a total of $131. So that's pretty good. It ends up being 29 cents per square foot for operation of the system. Some key points here. I had the coldest point in the greenhouse. I was actually back here when we hit 29.1 degrees. And this is really because I had no heat stored, and we had a very cloudy January. At that point, it was the cloudiest January on record, which may be perfect for an experiment like this. So I thought that was actually pretty good. I had a few plants in there. I think I had a banana. He didn't make it. I had a soursop or guanabana. He lost leaves, but did come back. But I didn't have a lot of stuff out there, so I was willing to take risks. I didn't have any other heat sources in the system. I have no backup throughout this whole year. So this is just what it did on its own without any other heat systems, no grow lamps, nothing like that.
Shannon, there are a couple of questions in the in the Q&A. Most of them I think you can hit later, but one that might be more relevant right now. Where is the temperature being taken in the greenhouse?
Yeah,
Well,
yep. So this here is in the center of the greenhouse. So I have the temperature sensor. This one's about 4 foot above grade, above the ground. I do have sensors in other areas as well. And I see pretty uniform air temperatures in there because when the fans are moving, they're moving quite a bit of air and stirring everything up very well. So it's, plus or minus 2 to maybe 4 degrees across that growing area. I did choose to put, if I was growing any colder hardy stuff like cauliflower, broccolis, put those out towards your walls. They want it cooler anyway. So it's a good place to keep them, keep your warmer things, maybe your tomatoes or your peppers or your tropical chocolate trees towards the middle. Okay, yeah, that's my last number on here. So you see our temperatures are getting really high on these sunny days here. Even when I seen it starting in February, I was getting above 100. And at this point, I did not have the vents opening because I was greedy with my heat and wanted to capture as much of it as I could. But I just got the wiring and stuff finished for them here towards the end of February or early March, and got those upper vents, these two up here, automated. So they'd kick in and open. I think I had it at like 90 degrees or so. And you can see that really then cut off those high temperature peaks. Yeah, didn't really have temperatures that high again, even throughout the summer. Up until August and late August, that's when I did start to see that the top vents were not enough. And then I did have to use the bottom vents really just for August and a little bit of September. So yeah, not a lot of time. And so I would do things differently in regards to the lower vents, because it's just not worth the cost and the effort. I didn't automate them. I just opened them and left them open during that time period. But other alternatives for reducing the solar gain a little bit would be like the cloth stuff. Dan might have to help me with the name of that. I forget now. The shade cloth is probably what I'll add on this year, so I don't have to open the lower vents. Yeah, so then kind of looking at this, now I've got lots of heat stored, and how's it going to do throughout the winter time? So you can kind of see here, we're in early October, late September. I've got the heating thermostat set to 60 degrees. So the climate battery has enough heat stored. I'm able to maintain a 60-degree minimum temperature up until mid-October here. And we had a pretty good cold spell where temperatures were getting low. And I ended up using up that heat and then set the thermostat down to 50 because I was burning through heat too fast. And yeah, and then really I was able to keep it a low temperature of 50 up until about mid-December, which was awesome. So the tomatoes were producing up until mid-December with no other heat sources, which is pretty exciting. And yeah, so then here towards mid-December, our days are getting short. Our amount of sunlight that we can get is at the lowest that we'll see for the year. I set the thermostat down to 45 to kick in to heat the system. So that's kind of an overview of the temperatures throughout the structure for last year. Any other questions on this slide topic?
No, there's lots of other questions though.
Yeah.
Some of them we can probably go through pretty quick here. Is your polycarb double wall?
I have triple walled polycarbonate on the glazing side. Yep.
Right. Any reason you chose dirt instead of gravel or sand for your battery medium?
Yeah, I used dirt, or horticulturist might call it soil, because that's what I had. I use soil because that's what I had. There is a slight benefit to the amount of heat that you can store with rock or gravel or sand, but I wanted the flexibility to be able to grow in the ground because if I want to plant a cherimoya tree, they actually do okay in pots, but they'll do better in the ground. And so that was one of the motivations. I think the biggest thing is flexibility. Because you can put your plants in pots, you can put them in the ground. Whereas if you have a sand or gravel or rock or something, you wouldn't be able to do that. Let's see.
And I don't know if you want to answer some of these or ask some of these questions because you might be covering some of this stuff later on too.
Yeah, to compact the soil between layers. Well, we had outrageous amounts of rain that year. So the rain, when we get 6 inches of rain, that compacted the soil while I was building it. So that happened on its own. But yeah, it is typical to compact your soil when you're building that. What would the results be if I use 2 to 3 inch stone? I don't know. Dan's collecting that data.
Although it's a totally different greenhouse, so
oh yeah, okay. We
hard
might
to extrapolate. I don't know.
That's a great question.
Yep.
There's the stem walls. Yeah, they were 4 foot. The foundation walls were 4 foot deep. And how much heat rose up? All right, we'll talk about heat soon enough. So let's see, next slide here. So temperatures of the storage medium. So I have a bunch of sensors tracking performance characteristics. So this here, this graph shows 2 sensors. You can see this here's maybe a side view from the south looking at the system. These sensors, one is located 2 feet below ground and one is 4 feet below ground. And these are along the south outermost wall. So these should be the coldest temperatures of the storage medium out along the wall on the inside, but where it's going to be the coolest. And so some things to note in the data, they track pretty similar, but during the summertime, you do really see a difference between the 2 foot and the 4 foot depth. So the dark black is the 2 foot, light gray is the 4 foot. So as you go deeper, it's cooler, which makes sense. In the summertime, the lower tubes remain cooler because the heat is conducting out of the bottom of that battery into the ground, and our ground below the structure is cooler. So you do get more cooling effect from your tubes that are 4 foot down than you will get from your tubes that are only 2 foot down. And then if we look at the opposite end of the year, in the wintertime, we see the opposite gradient occurring, where the 4 foot tubes end up being warmer than the bottom tubes. So the lower tubes remain warmer and get you more heat. Your lower, deeper tubes will be a better source of heat and cooling for you throughout the year. Something that's interesting, really, what's happening here is once you exhaust or consume maybe all of the heat that you had stored, the climate battery system then doesn't just stop functioning. It ends up functioning like a low-grade geothermal system. So you're not just stuck and not having any heat. You just have not as much as a climate battery can handle when you're not getting enough sunlight to store. So yeah, overall, the shallow tubes provide faster heating and cooling. You can see that here. I kind of highlighted the trends. So the black one again is the top layer. When you are extracting heat, it loses its heat faster, gets cooler. But then when your sun comes back out and you're able to store heat, it does recover faster. So it's a quicker, faster heat. Whereas your deeper one gives you a slower, greater quantity of heat storage.
Shannon, did you insulate the bottom of your battery?
No. The foundation's insulated like the diagram where it got 4 inch along the concrete and then the 2 foot frost skirt along the perimeter. So no insulation below it. I think, overall, I don't think you would want to. For one, you want your moisture to be able to escape out of there, but you would prevent it from functioning like a low-grade geothermal once you exhaust that heat that you have stored. So
I'd agree. It was one of the questions in the Q&A.
yeah, yep.
Do plant roots interfere with buried tubing?
Well, that's a good question. I don't believe so. So the tubes are perforated, and it's really like the air pruning you would get on a pot when you plant your pot. So the air flows in there, and the roots aren't going to be very happy living in the pipe.
Somebody asking, what's the closest major city for pulling climate data? He was expecting.
It is Brookings, which is 5 miles away.
And how much did it cost?
Let's see. The whole structure was just under 20,000. It was 16 by 28. I did most of the labor myself, except for pouring the concrete foundation.
Shannon, we've got like 9 minutes left.
Yeah, okay. Here's a slide on heat, storage, and cooling. Someone asked about how much it heated and cooled. You can see that there. This is in kilobTU. You can check that out. When the ground is cool, you can absorb a lot of heat for cooling. By the summertime, you get less cooling than you could get in the wintertime, of course. And in the fall, we get a lot of good heating because we have a lot of heat banked up and stored. So maybe covering a little bit of design guidelines here. So basically I broke this out into growing zones because we might have growers from all over the place. So this graph shows the time to return on investment for different insulation types. So this here's what I did was design D with insulation on the here and the frost skirt. And really what I found, if you want a 2 to 3 year payback on that for zones 3 and 4, this is a good option to go. If you're down in zone 5, you wouldn't want to go with that. You want to go with maybe just the 4-inch. And if you're down on zone 6, just a 2-inch should be sufficient for you. So here's some of the assumptions that go into that calculation. So you can check those out when you watch the recording of this. Heat exchanger tube length is a question that folks have a lot. And I did a bit of comparisons here on different airflow rates. And here we have a graph that shows my fans were variable speed. So I did some tests where I ran them. I had different fan speeds for a while to characterize the amount of heat storage I could get at different fan speeds. And what I did find was that as far as I could turn the fans up all the way, I didn't see a point where I was getting diminishing returns on the amount of heat stored or extracted. So that shows there's more room for airspeed increase there in CFM. This here shows the temperature difference from the ground temperature, basically the climate battery temperature versus the incoming air. As that increases, the air coming out of the tubes increases a little bit, but it's really not a lot. So I was surprised I was getting pretty good heat transfer from the air coming in. It was only a couple degrees above the ground temperature by the time it was coming out. So really what you can take from that is that the 4-foot tube length worked out pretty well. So you really want to minimize the tube length because once the air reaches the soil temperature, there's no more heat transfer going to happen. So too long of tubes is not a good thing. And I found a really exciting graph I'll share later on that. Another thing was the climate battery intakes. Everybody knows heat rises, but that's not true. Hot air rises. I observed that the intake temperature was quite a bit lower when I was storing heat than my main center air sensor. So that was maybe not what I was expecting, or definitely not what I was hoping for. So this here's shows of the fan, and I actually ended up disconnecting that down the road But I added some temperature sensors at different heights to measure what the temperature stratification was from the ground going up. And so averaged out over the course of a month during storing time periods, which is when you want to be pulling in the hot air, I seen this this temperature gradient from basically the ground level, 4 foot above the ground. I had a 3-degree increase from ground level. And then by the time I got 10 foot above the ground, actually it was a little bit cooler with only 2.5 degree above the ground temperature. So it was really pretty minimal temperature stratification. And really the reason for that is because you have enough airflow moving through the system that it doesn't really allow that natural buoyancy of hot air to take over and control the stratification of the system. So if you have a well-sized system with good airflow rates, you're going to see very minimal stratification. And so what I did end up doing was remove that extra ducting and just put a 90-degree elbow on the top of those because I was able to get a little bit warmer air going into the tubes. So some things I do differently, I would decrease the spacing of the heat exchanger tubes, maybe to 14-inch on center, so that I could store heat faster. In the February timeframe, I was hitting 100 degrees without venting, and that's definitely heat that I could have stored and used if it could store it fast enough. What we have happen in the wintertime is we get a lot of sunlight for a short period of time. So it's really essential that for that short period of time, you can capture that heat while you get it. I would keep the 2 foot depth for the top layer so that I didn't have any issues with maybe cultivator hitting a tube or something like that. Then manifold tubes, I use 6-inch. I took a hit and a lot of airflow by using a 6-inch, and I kind of knew that at the time, but I needed to get it done, so that's what I did. Then I'd also consider using a non-perforated manifold. I did observe that I had some air leakage through the manifold because it was perforated. So it maybe doesn't hurt with the heat loss, but what I see was that the soil would dry out much faster near the intake manifold because air was percolating through the soil and drying out. So if you're growing in the soil, that's a challenge. You have to water that spot more often. Now, this here's something I found actually after the fact. Was this research paper here back from 1997. It's an awesome paper. Definitely encourage you to check this out. But these guys did numerical simulations based on some field tests that they did near Quebec City, Canada. And I took some of their graphs because they're all in metric units that I'm not used to. And I converted those for you guys. You could kind of check it out and a little bit easier to grasp and understand. So things are in inches and BTU instead of megajoules and cubic meters. So really what this shows here is the storage capacity of the system per day. So how much heat you can capture per day versus the flow rate, the CFM through a 4-inch corrugated tube, and the different tube spacings. So actually what I would have constructed was a 24-inch, which would be somewhere around here. So if I wanted to store a lot more heat per day, by moving those tubes closer together, I could get double the heat storage per day capabilities by moving to, say, a 15. So this was a really awesome graph. That's really one of the questions I had was, how close is too close? How far is too far? I would say 24-inch, at least for my situation, my application is too far apart, and there's a lot of gains to be had. Of course, I didn't see freezing. I'm growing things just fine, but I could grow warmer things. Now, there's a bunch of trade-offs to consider, though. So, maybe a 9.8 or 10 inch is not the best route to go. Closer tubes cost more money. Closer tubes means you got to have more fans to get the same amount of CFM. And closer tubes, you lose more of your thermal mass. You don't have as much place to store it. So there's trade-offs there that you probably don't want to be going way to this far into this. The next big question that this paper answers, which I think is really awesome, is what is the best tube length. So this graph is similar to the other one where we have the storage capacity per day on the left side here. And we have, again, tube spacing distances shown here and different tube lengths. So as you can see, the shorter your tube length is, the more storage capacity you have because of the temperature gradients that you have throughout the tube. So there is maybe some diminishing returns on this. As these, the difference between a 50 and a 90 and 100 is not maybe that much. So why would you go with a long tube? I don't know. There's maybe some trade-offs, not many. Shorter tubes might change your manifold layout, but in general, you want to go with as shorter tubes as you can. With 10 is probably pretty short. I wouldn't probably suggest going that far, but 15 or 14 that I had worked really nicely. So that's maybe a lower end of that you might want to go to. You really want to try to avoid going with long tube lengths because it takes a lot of energy for your fans to push that air through there, and you don't get much benefit for doing that, or you get no benefit for doing that. Got some other things that do differently. Let's change the next slide. There we go. I would eliminate the knee wall that I had on the south side with the intake vents. The reason is because I wanted to improve the light level on the ground for growing during the wintertime, get some shadow down there. Wasn't good. The top vents are great because you don't get as many pests. Definitely you don't have mice flying in there, which you can have in the bottom vents if you don't have screens on there. Insect problems are less through the top vents than the bottom vents. I plan to use shade cloth for that short period of time, so I don't need to use the bottom vents this year. And I had a lot of condensation and glazing and didn't have a chance to put in a better maybe management system for where that condensation goes. The roof structure, I'd probably not go with the clear story system. I would still keep upper vents, but it adds a lot of complexity to just the construction of it and more cost to do that. And I think having the vents just in the top roof on the north side would be much easier. I'd have a little bit less surface area, so less heat loss. And I think it would actually be easier to seal and keep the water and ice out of the vent seals. So yeah, a lot of things I'd like to do and learn more about. Looking into reliable automatic insulating curtain to reduce the glazing heat loss. We still see a lot of heat loss even through a triple wall polycarbonate. Is not a lot of insulation level. So that's a big opportunity for improvement. Definitely alternative structure designs. I think the deep winter greenhouse farm scale layout is pretty nice. Or CSG, here's the Chinese solar greenhouse. If you're not familiar with that, Google that, check that out. It's actually pretty similar in shape, maybe to the farm scale structure. Looking at more layouts for climate battery tubes. What's the best way to lay out the manifolds to get even more improvements out of that? And the biggest issue, it's too small. I got more things I need to grow. So that's overall summary. Any questions that we should cover now? How much did this cost? I think we covered that. Bob asked, what's the best material for insulated curtain? That's a great question.
I can maybe chime in on that. I would say there's no definitive answer because there's always challenges with an internally mounted curtain, with it competing with structure and getting good air sealing, so you actually have the insulated benefit of the curtain in place. On the exterior, of course, there's all kinds of weather issues and UV degradation, as the case may be. And then deployment mechanisms, do you have it go automatically, or do you have to go out there every day or twice a day to open it up and deploy it? So I just applied for a grant to work on this exact question. So everybody knock on wood for me. We'll try and get this answered. Bubble wrap, yeah, that works. And our value of bubble wrap is about 1.8, something like that, for the just regular thickness little stuff. So,
Oh, did anybody know what the flower was?
What's that? Oh yeah, a couple people got it. Yep.
Okay, good. Yeah, I took this this photo actually yesterday. It was my first passion fruit flower that opened up. So I'm pretty excited. This vine is huge and massive across the north wall, and I was concerned. I planted it last spring and wasn't sure how long it would take, but this spring it's gone wild and has hundreds of buds. And this is the first one that's open. Unfortunately, it's about 12 to 14 feet up in the air. So I'm on a ladder pollinating this because all the bees are still sleeping. So that's why there's another ladder over here in the background. So it'll be an interesting pollination experiments.
If I can share my screen, Shannon.
Yeah, go ahead.
I've got a couple things to share here. Hold on. So a couple things that came up during Shannon's presentation. One about what you can grow in there. I just really appreciate it. I've had the opportunity to go to Shannon's greenhouse and check out what he's growing in there. And it's awesome and inspiring. And it's such a wonderful departure from just like, the purely business oriented, we're going to grow as many salad greens in a winter greenhouse as we possibly can kind of approach that, many producers have been looking at. And I love the exploration of just trying to figure out what else we can do in these, because, we're creating these new microclimates in this area that, previously we hadn't really had access to. So I think it's just really fun. And also, an anecdote about bees. I was down at the Lake City Deep Winter Greenhouse, which you'll see some pictures of in just a second here. And they actually, this was early March, and they had their vent windows open, but they hadn't put their screens in yet. And they're growing some citrus in there. They've got 7 different varieties of lemons and some dwarf grapefruit. And actually the bees were waking up at that point down there because there had been enough heat, but there was nothing else blooming, of course. And so they caught scent of the citrus plants and were flying into the ventilation windows of the greenhouse, coming in, pollinating the citrus, and then leaving again. And so the cool thing was, like, they're not getting any bugs in the greenhouse besides the bees. And the bees historically, this is a really challenging time of year for them because you get, steep or drastic temperature drops and no food for them. So I never thought that the deep winter greenhouse would be pollinator friendly, but here we are. So I've got a couple things here. I told my wife I'd be done by 8 o'clock, everybody. So I'm gonna just try and race through these. I'd say the biggest thing about the DWG V2.2 that we designed in partnership with the regional partnerships is that it uses a rock bed for thermal storage. I had seen all of the GAT type and SHCS systems that are putting plastic ducts through soil, and it just didn't make any sense to me. Why would the heat want to transfer through this plastic walled ducting and make its way into the soil, which is not a great conductor either. And so I just kind of went on an exploration of different types of thermal storage and thought, hey, let's try this. We're excavating down that far to get below the frost line. Let's just, take it all out and fill it full of rock. The premise being, rock would be relatively cheap. Come to find out that's not always the case. But that was the intention. So this was not the low-grade geothermal. This is operating more on this approach, however, using rock bed and eliminating the ductwork, right? And so that's one of the biggest things here, is that I was trying to get actual direct air to medium contact rather than moving air through the ductwork and relying on some kind of thermal exchange through the walls of the thermal exchanger, which you could look at the duct as being. And what are some other elements of this? Of course, the hot air goes up to the peak of the greenhouse. It gets drawn in and down into this solid wall intake plenum. And then goes down into this perforated horizontal tube. It gets basically drawn out. It's negative pressure down in this in the rock bed because everything is basically circulated by a single inline. It's basically a radon fan in the exhaust side of the rock bed, and so the air is circulating like this, and it's getting pulled through and then pulled out of the rock bed with this. One important thing to note about this is that on top of the rock bed is a cap. It's a sealed cap, and this acts as what is called a packed bed, or a sealed plenum, right? And where it's basically part of the duct, only it just happens to be filled with rocks, right? So it's forcing the air to move directly over the surface of those. Here's what it looks like in section. A couple modifications is that I would recommend putting the plenum down as low as you possibly can go on either side of these, because of stratification. Hot air is going to want to, even though it's kind of, getting drawn through here, it's not going to take the shortest path. It's actually going to rise as it comes up out of here, and so we'll get a little kind of bubble of heat moving up through here. So I would push that down as low as you possibly can. Here's what it looks like going in. This is from the Bemidji Community Food Shelf installation. You can see their 4-foot stem wall here. Here is the intake duct. This, of course, will get more ducting that'll go up to the peak of the greenhouse. And then this is perforated, so it gets drawn through. It moves its way through the airspace in between the rocks and gets drawn into this perforated tube over here and gets pulled out of all that by the fan that's mounted on top of there. Here's another picture of the rock actually being placed. They have this big fancy conveyor belt placing machine, which saves a ton of work besides shoveling rock, which is not the most joyful task. Also of note here is some of the temperature monitors. We put temperature sensors in these rock beds to try and get some performance data, which I will get to in just a second. Here's what it looks like with the sensor cables run over the top of the now filled rock bed, and the reinforcement has been placed to put on the concrete topping. And this is the seal for the top of it. You can also use different types in this greenhouse. This was the first one that was built at the Organic Consumers Association up in Finland, Minnesota, just off the North Shore. They actually put in a compacted soil seal cap on top of the rock bed, and then they put raised beds on top of that, and so they're effectively growing in the soil. I don't anticipate they're getting much root penetration down into that, or it acts as the the air. Let's see. So what is happening in down there? We know it's working. It's banking heat, and it's able to make it through the wintertime, but we don't still know exactly what's going on down there. We've currently got a Fulbright scholar looking on the data points from this particular greenhouse. This is the one in Lake City, the one that I mentioned that had the bees coming in and pollinating the citrus plants. We have something along the lines of 256 distinct temperature sensors on each of these rebar columns here. And so it's just an incredibly immense set of data. So he's coding basically to be able to parse through this stuff and figure out what's going on in there. The early kind of preliminary takeaways that he has from this are two things. And I want to preface this by saying two main things. One is, this is from 2 overcast days. It's 2 days, consecutive days, but they were both cloudy. Okay, so this may not be indicative of what's happening during a couple sunny days or in a period of sunny days that go into cloudiness. We don't know. Okay, that's what he's working on right now. So what's happening? Most of the warm air appears to be moving right through the middle of the rock bed. So it's basically coming down the bottom of that intake plenum and exiting pretty close to where it's coming in through. And even though they're pretty small holes, and conceivably it should be pretty much equalized pressure along that whole distribution plenum, that's not what's happening based on the measurements. It's kind of moving directly through the middle of the rock bed, not making it out to the sides, which is unfortunate because we went through a lot of effort to try and, make this big rock bed and encourage air to move throughout the rock bed. We've, to utilize the entire thing. That's really the point of this, right? Any place we're putting in ductwork or a heat exchanger or trying to get air movement through there, we want to have, equal distribution, air movement through there. So maybe we need to adjust the plenum distribution method. So that question that just came up, have you thought of load balancing the plenum? That's exactly what this would be. And so that could look differently. So whether that's about changing the density of perforations in the plenum so that maybe there's Not as many perforations toward the middle, where the intake plenum meets it, and have more towards the edges. It's kind of counterintuitive though, because there's some Bernoulli principles that would say that we should get more air movement at the ends of the plenum, which would be good actually. We'd like to see a little bit more air movement in the edges than in the center even. So yes, what could you do? You can put in more systems, right? So you could have 3 vertical intakes, but I would separate them, have them in different groupings of transit ducting rather than, or separate, how can I put this, baffling, so they're separate systems effectively, so they're not all feeding into the same plenum. So what else? The other big takeaway is that the northernmost half of the rock bed, that is where the hot air is coming down into the rock bed, that seems to be fluctuating with temperature, right? That seems to be actively banking and discharging heat. Whereas the southern half of the rock bed seems to be pretty stable. While this is good, I mean, that's really what we want it to do, which is stabilize the temperature. It'd be nice to see a little bit more utilization of that entire rock bed section, right, from north to south. Hopefully we'll see a little bit more of that when we get greater fluctuations, i.e. more sunny days in a row. So that remains to be seen. I will keep you posted. Next steps, of course, sunny days and consecutive sunny days followed by cloudy days. So looking at how we load balance the plenum, this actually is the dryer in a car wash that I happened to notice about mitigating that Bernoulli effect. If you notice, this column is actually slightly tapered. So it's a variation on the trunk and branch system, as you might see in any kind of furnace layout, basically trying to equalize what's coming out of each of these. So that could be one way to look at trying to equalize the pressure. And otherwise, how are you maximizing contact with all of the rocks? I've gone back to this idea of maybe trying to like do a finger jointed thing so that you're getting more direct airflow through there. I still don't think the intake and exhaust tubing is the right idea here, but I don't know, maybe there's some potential there. So that'll bring me to the farm scale winter greenhouse a little bit. You're probably familiar with this. This is the latest kind of take on increasing the size of the greenhouse and trying to maintain some reasonable upfront capital expenses to get winter production. And so the early kind of illustrations showed a very similar system to what we had in the V2.2 drawings or greenhouses. But after discussion with Shannon, made a couple variations and trying to do more of the Z-type layout that he's using in his greenhouse.
That would improve the rock bed uniformity too.
This would, if we had ducting through there?
On your rock bed, if your intake was diagonally opposite of your exhaust.
Oh, yeah, right. That makes sense. It's still going to take the path of least resistance, which we'd still not know exactly. But hopefully that would be equalized through the entire rock bed. In short, this is actually aligning quite nicely with the graphs that Shannon showed earlier as far as spacing in between the ducts and the length of each of these transit ducts, and then actually using an 8-inch solid wall manifold on either side, and then stepping down to a 3-inch transit duct in the middle, so that we're getting really good balance of surface area, so that we're maximizing our conductivity, right? Which is really what we're trying to aim for in trying to get heat moved into the soil, right? So we're looking at 5 separate systems within the greenhouse. This dimension is 20 feet. This long dimension is 60 feet, roughly. That question about having more intake ducts, this is basically trying to answer that. So these are separate systems. Each one of these will have a circulation fan, all operating in this kind of Z layout. The couple last things I'd like to just bring up, because I think they're a little bit peripheral, but they're important. One is the operating control scheme. And I think this actually refers back to some of Shannon's slides quite nicely about those periods of time where the fan was either on for heating, that is, drawing the heat out of the rock bed, or it was on to cool, basically drawing the hot air down out of the greenhouse space and charging up the rock bed, or it was simply turned off where the temperature in the greenhouse was groovy, right? We just want to leave it there. Don't mess with it. So that's this point right in the middle. Of course, these temperatures are kind of arbitrary. They're just kind of a guideline, depending on what you're growing or, your exact conditions, you might have to mess with this. But essentially, we've got this point in the middle where the rock bed or the circulation fan is not going at all. Then down here, we've got this point where, yes, you probably have a backup heater or you need a backup heater that's going to be kicking on, but that's only happening in extreme cases, right? And hopefully we've got some stepping of both your fan speeds and your heating capacity. Up here on the high end is we want to make sure that we are banking as much of that heat as we possibly can before we start exhausting it out the window, right? So make sure that we have as much airflow as we can, properly sized to our ductwork system, so that we're getting as much heat captured in there before we start opening the window. We don't want to be opening the window while we're circulating that stuff in there, right? Because then we're actually starting to draw some cooler stuff down in. Then we're losing our opportunity to put that heat down into the rock bed, right? What else? Oh, last thing was a question that kind of came up earlier, which was about radiative absorption of different colors, essentially, and the balance between what plants like and what we are trying to do to store heat. What you will probably find quickly is that it's not actually the heat that's the limiting factor in growing in our northern latitudes, but it's actually the amount of light available. And so the white interiors or lighter colored interiors generally are better for bouncing that light around, making the plants happy. And we can store heat in other ways rather than in the walls of our greenhouses. So with that, how did I do? That was like 20 minutes even. Still.
Very good. That was fast.
I know, right?
That's why it's recorded. So
hopefully, yeah, good thing.
There's a question I wanted to bring up because it got answered in text and isn't viewable for you if you're not looking through the text. But someone wants to know which is better, the deep winter greenhouse 2.0 or the farm scale winter greenhouse up near Grand Portage area. So
which is better up there?
Yeah.
Okay. The short answer is I would say the farm scale with some variation, some upgrades. How about that? I would put on triple glazing. I'd put on a thermal curtain, and I would use multiple layers of like a GAT system or a SHCS system. How about that? Depends on how big you want to get too. I mean, that's the thing. It's like the V2.2 works great. It's fantastic, but it's spendy, and it's only, the growing area is only 16 by 24. So, it's like 450 square feet of growing area, which, even Shannon's is bigger than that. And he says he doesn't have enough space. So,
Yeah, it really depends on what you want to grow. If you want to grow tomatoes, you want to have a good 8 foot of height for those vines and stuff. So.
All right, let's see. Where's the best place to get trusses and polycarbonate glazing up in northern Minnesota? Does anybody know of a contact up there?
Trusses you could probably get custom made either from somebody locally or there's actually quite a few Chinese companies that are trying to export trusses for their Chinese solar greenhouses. So you might actually be able to look online. Shannon, I know you got a bid recently.
Yeah, I've gotten some bids from those. If you want to source something from China, try their version of Amazon, Alibaba. There's all kinds of pictures, and they're pretty good and responsive. I have not ordered through that route, but that's definitely a way to peruse what's out there.
But if someone wanted to,
and polycarbonate, you can order through your local big box retailer.
Yeah.
Or just order it online. There's plenty of retailers online that will just ship it to you. You're gonna have to pay a shipping.
Menards usually has it.
What's that?
Menards usually has it.
Yep.
Or,
Menards has a surprising.
Or there's a whole bunch of online ones.
Yep.
So if a thermal curtain is used at night, can you grow all winter? Or so, I'm sorry, can you take the system through entire Minnesota or northern climate winter? Can the system take you through?
Of course, I did it without.
Yeah. Yep. Yeah. I mean, there's a ton of variations, and there's people growing up, way northern Canada, so
Alberta.
Again, and they've got way more insulation in their walls typically, and they probably have, at least triple glazed glazing. So yeah, it depends on the energy balance, but of course, yeah.
So some people do use backup heat though. It's just if it's not very cloudy, you don't use very much. If it's cloudier, you'll end up using more, right? Have you looked at the rock bed storage from the New Alchemist Institute?
No, I'm not familiar with that project.
All right, there's some Googling for tomorrow. Where's the best place? Why only use plastic tubing? Could you use different material? Like for the
Like what?
Metal won't last all that long.
Yeah, that'll rust.
Concrete. I'm not sure what else would there be.
Well, I know that the early Chinese solar greenhouses used actual like ceramic tile, like the hollow grain tile stuff to move air through. And so you can use that. I mean, it's a great massive material. It actually does, it stores heat. But yeah, I mean, it's harder to find. I don't know if you'd be able to find it too easily. Plastic is just, it's cheap. It's pretty strong. It's durable.
It's available.
It doesn't conduct heat the best, but
yeah, it's so thin walled. The effect isn't much for the plastic.
Yeah.
So there's a question about the triple wall polycarb. Can it curve like the double wall for that farm scale design? Where do you get it? People talk to you about the flat poly. We're not very helpful with application questions. So you talk a little about the curving, so the flexibility.
If you go to the PowerAm website, I think, is it Sunlight is the actual, okay, let me back up a little bit. Almost all of the multi-wall polycarbonate panels are made by one of two manufacturers in the entire North America, okay? Everybody else is just redistributing it. So just go to the PowerAm website. They're the manufacturer. They've got cut sheets that talk about, bending radii, right? And so the bending radius of the farm scale winter greenhouse is pretty much exactly at the limit of the bending radius for the triple wall polycarbonate. Okay, I think it's like 52-inch radius or something like that.
Is the farm scale double or triple?
The farm scale is specified as double, but you could do it with the triple.
Okay. Yeah, I guess behind my head there, mine's triple wall, and that is at the low end of the acceptable radius for triple walled. That gives you a view of it.
You mean you could go farther, or that's about the limit of it?
That's the limit.
Okay.
Yep. At the steep part of that curve. So you push it any farther than that, it'll still bend, but you might get it cracking or warping and stuff during hot, probably mostly the cold, because it shrinks the most and then it's going to have issues in the cold.
All right, can you spell that name out there so people
PALRAM.
What are you at a time? Dan, you spell it.
Oh, I typed the answer.
Oh, can you just spell it out for people in case they aren't seeing the
PALRAM, PALRAM.
Okay, thanks. Let's see. Look at the plenum design for an air curtain incinerator. It uses a constructed rectangular box that gets narrower to the far end.
Yeah.
Here's a link to the New Alchemy Institute for everybody.
And thanks, John, for the link to the New Alchemy Institute.
And with that, all the questions are done. We will get your PowerPoints, your slideshows, and put them up online, as well as I see that this is still recording, so that's good. So we'll get the recording for this presentation, put it up online in addition to your PowerPoint, so that everybody can dig through it and get all the information they need.
We're only half an hour over schedule.
Yeah, Thanks everybody for sticking with us for the extra half an hour. Those of you who did, and sorry if it was stressful for the extra half hour, but we'll maybe do some more webinars on deep winter greenhouses and winter solar greenhouses in the future. So look for the emails and the Facebook notifications or however you found out about this. And with that, I'll wrap it up. Thanks everybody.
Good night, everyone.
Good night.